Lesson 10.1 is going to begin with exponential functions. So we are going to have these relationships. Remember, a function is just an equation, it's just a relationship that are based in exponents. So for example, an exponential function like y equals 2x. The base is a constant, the 2 would be the base, and the exponent is where our variable is. And we're not used to seeing variables in our exponent position. So let's figure out how to handle a graph like this. So to sketch the graph, we need to make an XY table. So we are going to pick values for x, put them in, and see what happens. So if we let x be -3, we get 1/8. Because remember, the exponent rule of a negative is that you do 1 over that value. And so you can see the table continue until we get a good pattern. And the pattern we see emerging is that right here we have our y-intercept, and then it's smaller on this side. You'll want to maybe do decimal approximation so you can see the graph, but we'll see it's getting closer and closer and closer to the x-axis and then growing exponentially. And what we're going to see happen is that our domain is all real numbers. Remember, domain is what you can put in. Okay, so that's our x values. And the range is our outputs, or our y values. And what's going to come out is only positive numbers. So to tie back to our old unit, we are going to see an asymptote develop here at the x-axis. It's going to come down close to, but never touch or cross that x-axis. So what are some general things about these equations? It's going to have this form, y equals ab to the x. And this is critical because your a is going to be your initial value. Okay, it's your y-intercept. Your b is your rate of change. And there are some rules about that which we'll talk about in a minute. But this is the base form that you need to know. So in general, an equation of the form y equals ab to the x, here's our restrictions. A can't be 0. Well, that makes sense because the whole thing would be 0. B must be greater than 0, so that rate of change has to be constant. It can't be 1. Okay, so those are your restrictions. So it's continuous and it's 1-to-1. So there are no holes. And for every x you put in, there is a unique y that comes out. There's no doubling up. That's what 1-to-1 means. The domain is always all real numbers. The range, I'm going to skip down here, is always positive numbers if a is greater than 0, and it's negative numbers if a is less than 0. And we'll look at some examples of that. We've already talked about the x-axis being an asymptote. The graph always contains this point 0a, that's the y-intercept. That's what we talked about right here. And this last one. The graphs of y equals abx and y equals a times 1 over are reflections over the y-axis. So if we flip, here's our graph that says y equals ab to the x. This one is y equals a times 1 over b to the x. And really what we have going on here is what's called a growth graph if b is greater than 1, and a decay graph if b is between 0 and 1. two types of graph, growth and decay. If your values are getting bigger, it is growing. If your values are getting smaller, it's decaying. And here's the bit about the bases. The base of an exponential growth function is a number greater than 1. The base of an exponential decay function is a number between 0 and 1. Still not negative, so really we're talking about a fraction or a decimal. Less than 1. So in summary, here we go. If a is greater than 0 and b is greater than 1, the function y equals a b to the x represents a growth function. If a is greater than 0 and b is that fraction or decimal between 0 and 1, then this same base graph becomes a decay function. So for example, y equals 2 times 3 to the x versus y equals 2 times 0.4 to the x. This would be growth because this value right here is greater. In this one, we look at this value right there, and that means that this is a decay. This number out front has nothing to do with growth or decay at this point. So, naming them. So here you see the same thing looking at these models. And if I look right here, since that number is something other than a whole number or a number greater than 1, it's a decay graph. If I look at this number right here, that is a growth graph because it's greater than. And if I look at this number right here, yes, it's a decimal, but it's a decimal greater than 1, so it represents growth. Again, this constant a out front has nothing to do with growth or decay. So, we need to graph these. Actually, we need to write the equation. And writing the equation is very simple. It's actually a two-step process. We can use the y-intercept and one other point in the graph to write the equation. But it takes 2 steps. So what are those 2 steps? 2 steps. It's a lot like our direct variation, indirect variation, and joint variation problems. So one, you use the given information to find b. That's your rate of change. Then you use b and a to write the equation. And remember, equations always have x and y in it. Okay, so 2 steps. So here we go. In 1983, there were 102,000 farms. So there's one data point. But by 1989, there were 80,000. There's our second data point. Now we aren't going to put years into our equation because that would be too cumbersome. But we do need to figure out the initial value. So 1983 is our starting point. So our time is 0. That means the initial population is 102,000. So this really is giving us this point. It is our initial value. And then they're going to give us some other value down the line. So in 1989, what is x? It's 15. It's 15 years after our initial point. We get that by subtracting. And our population is 80,000. So this gives us the ordered pair 15, 80,000. So our inputs, our domain here are years, our range, our outputs are number of farms. We know it's decreasing. We know that this is a decay graph. Okay. Okay, so we know in our heads before we even start that our b value has to be less than 1. So it's a nice way to check ourselves. So here we go. So here's our base value. This is step 1. We insert 80,000 with its partner 15, and then 102,000 is our initial value, leaving b in. Divide both sides by 102,000. Now to undo the 15th power, we take the 15th root. You can go to your calculator and do the 15th root. And each calculator has a little bit different way to do that, but we can figure that out. Then in step 2, b becomes this value right here after you take the 15th root. So then I go back and I insert my a, my initial value, my b, and I leave y and x in the problem. Now remember, order of operations, you have to do exponents before you can multiply. So you cannot simplify. This would have to be done first. So you cannot multiply 102,000 times 0.98 to simplify this. So then once you have an equation, then you can figure out some things. So suppose the number of farms in Minnesota continues to decline at the same rate. This is our rate of change. What would happen? Well, if this is our x, so we take 2010 minus 1983, so 27 is x. We use our equation, we put 27 in, we crank out the math, there would be about 59,000 farms in Minnesota. Now, this is review. Since the domain of exponential functions includes irrational numbers, the properties apply. And so in quick review, if you have a to the nth times a to the nth, like bases being multiplied, you can add the exponents. If you have like bases, base raised to a power, you multiply the powers. And if you remember, we also have the ability, if you have a root and a base to a power, you can rewrite that as a fraction where the numerator is the power and the denominator is the root. So simplifying problems like this is review. And I would say here we could even go ahead and write this as 2 to the 1/5 plus the 1/3 power using this one. And then we could write 2 to the 3/15 plus 5/15. We could write this as 2 to the 8/15, and it becomes an even more compact, simpler piece to use. Now, why does this matter? Well, not everything has the same base, but we are going to learn how to start solving equations that have variables in the exponent position. So the first thing we're going to think about is the fact, these rules. If the bases are the same, it makes perfect common sense that the exponents have to be the same. And so we could write a very simple equation to make that happen. So tune into part 2 for the rest of the lesson.